Washington State University. Go Cougs!
Welcome back to the course on statistical inference. In Module 3, we are going to look at some techniques for analyzing data, not necessarily with a class prediction in mind, but just trying to make better understand the data, perhaps just looking at the sensor data, not necessarily the class values. Specifically, we'll look at some dimensionality reduction techniques for reducing the number of features or dimensions in our feature vector, and clustering, which is a way in which we can partition up the data into well-defined groups that will help us to better understand various trends in the data. For dimensionality reduction, we'll look at two techniques. One is feature selection, and the other is principal components analysis. So in part 1, we'll focus on feature selection. There are several different ways of doing feature selection, and as you can see, they are implemented in the scikit-learn feature selection module, and these are the various methods for doing that. The first method is a method that removes features that have low variance. So in general, in order for a feature to be useful, we need to be able to, say, identify a threshold such that below a certain value for that feature is one activity, say work. Above a certain value is another activity, say play. So if a feature doesn't have a very high variance, then it's less likely to be able to distinguish between classes or, in general, distinguish different groups of the data set. In the extreme, if a feature value has no variance, in other words, it has the same value for every example, then it's not very useful to us at all, and we can remove it. So that's what this variance threshold technique does. You provide the threshold of variance such that you want every feature to have, at least in the minimum, and any features whose variance falls below that are then removed. Another approach, which does use the class information if you're ultimately doing a prediction task, and that is to look at the correlation between a particular feature and the class value. So features that are correlated with the class we're more interested in using, as opposed to features that are uncorrelated with the class. Again, in the extreme, if we had a feature that had an entirely random value, it would not be very useful to us, especially for predicting a class. So the select k-best approach to feature selection will compute the correlation of every feature to the class value, and then keep the k most correlated features, and of course removing the rest. Another general approach to feature selection, sometimes called the wrapper approach, is to try a subset of features and then do the actual learning, classification, measure performance, and see if certain subsets of features have better performance than others, and of course keep the subsets that do well. Of course, there's an exponential number of different subsets of features, so we typically take a greedy approach. And in particular, one technique in scikit-learn called recursive feature elimination basically systematically removes one feature at a time, as long as removing that feature doesn't degrade performance. And once they've eliminated all of the features that don't have a negative effect on performance, then the features that are left are generally a better set of features. In all three of these cases, in fact, all of the feature selection techniques, there is a transform method that once you've identified the subset of features, then the transform method will transform your original data into a new set of data that only uses those features. And so after we select the set of features that we want to move forward with, we'll then call this transform method on the original data, and that'll produce a new data set from which we can learn using the subset of features. So let's take a look at one of these. We'll use the first one, the variance threshold approach, and see how to do that in scikit-learn. So initially, again, as usual, we're going to import our read data method. We'll use the naive Bayes classifier to see what effect this feature selection has on its performance, and we'll be looking at the accuracy of the classifier using the accuracy score metric. So in addition, we'll also be importing the feature selection module of scikit-learn and using the variance threshold approach. The main parameter to the variance threshold approach is the variance threshold, and basically any feature whose variance is not above this threshold is then removed. Generally, this is a pretty high threshold for variance, but our features have a pretty high variance already, and so just to demonstrate getting rid of them, some of them we have a high value here, but generally you probably want to set that a little lower. Okay, so first we'll read in our data. Again, nothing different here. We've seen this before, other than the fact that we are reading in all the data, all 9 of our features. And then as a baseline, we will first run naive Bayes on all 9 features. And so again, we'll create an instance of the naive Bayes classifier. We'll fit it to the data, use it to predict the original data, and compute the accuracy of those predictions. And so that will come out as the accuracy for all features. And then in the next part of the file, we'll actually do the feature selection. So first, I'm just creating a list of the different feature names, and eventually I'll transform this list along with the rest of the data so we can see exactly which features were retained. So first, I'll create an instance of this variance threshold feature selector and pass in our value for the variance threshold. And much like the classifier, we're going to fit that feature selector to our data, which is essentially going to compute the variance of all the features and remove any features whose variance falls below the threshold. So that's when we engage this transform method. Again, we pass in our original data, and that's going to transform that into a new set of data where it's removed all of the features other than the ones with sufficient variance. Likewise, as just kind of a trick, I'm going to apply that same transform to my list of features, and that will essentially retain only the features that weren't removed. And so by printing out that list, we can see which features survived the feature selection process. Lastly, we'll go ahead and create a new version of our naive Bayes classifier, but this time we'll train it on the new data instead of the original data, but of course with the same class values. And then we'll do prediction on that new data using this new classifier, measure the accuracy of the prediction, and then print it out, ultimately to compare to see if the feature selection had a positive effect or not. Now you can see the output down here, the features that survived, and we see that the accuracy did in fact improve. But let's go ahead and run that for real so you can see that in action. So again, here I am in the directory with all of our source code that comes with your course materials, and I am interested in the feature selection program. So we'll run that. And sure enough, you see the same output as we saw in the notes. So the naive Bayes classifier on all of the features gets about 95% accuracy. But with the feature selection, by removing low variance features, we see that only 4 of the 9 survived, the pitch and the 3 rotation features. And then if we run naive Bayes again using just those features, we see that the performance actually goes up. And so in this case, the feature selection was beneficial process to run. And in general, in much higher dimensional problems, feature selection is very useful. Back to the notes. So that's all we're going to do on feature selection. Again, there's a large number of different feature selection techniques, and we just scratched the surface, but they all generally follow the same process. And so you can try out others and, of course, tweak the parameters in order to choose the best set of features to maximize performance. So next, we'll look at a different approach to feature selection, which actually computes a new set of features, and that's called principal component analysis.